In this video, we're going to take a look at calculating binomial probabilities. First of all, let's take a look at what exactly is a binomial situation. We need to make sure that the thing we're looking at is a binomial situation so that we can apply the model and so that the formulas work correctly. So, first of all, we need to be looking at each trial or each thing that's occurring having only one of two outcomes that can occur. Now, normally we talk about these being success and failure. That's just like a generic term. But you could also think of it as the thing you want to happen and the thing you don't want to happen. So at each trial, only one of those two things can occur. Now, all the trials are independent of each other. So what happens on the first trial has no impact on what happens on the second, and so on. The probabilities of success and failure don't change from trial to trial. So if you're talking about tossing a coin, your probability of a head is a half, and that's the same all the way through, no matter how many times you toss the coin. It doesn't change. And the other thing is that there's a fixed number of trials. So that just means that from the outset, we might say we're going to do this thing 5 times or 10 times or whatever the number is. And as you go along through those trials, it doesn't actually change. It doesn't all of a sudden change from 5 back to 3 just because a certain number of outcomes occurred. That's an example. So some examples of binomial situations would be tossing a coin 10 times. So in tossing a coin 10 times, the things that can happen, you might think of success being a head, failure being a tail. Each toss of the coin is independent of the others. The probabilities, the outcomes don't change. And we've said that there's 10 times that we're going to toss the coin, so it's a fixed number of trials. Another example might be guessing the answers of 10 multiple choice questions with 4 options in each question. I talk about where this general formula for the probability of a binomial distribution comes from in a different video, but for the purposes of this video, we're going to take it as a given. So assuming we have all those things checked off from the previous slide, we're going to say, given that the probability of a success in any trial is some number p, the probability of m successes in n trials is given by this equation. So the probability that x, our random variable for the number of successes, is equal to m is given by n choose m. That's the first thing you see there in parentheses. N choose m. I'll talk about that in a moment. Multiplied by p to the power m. So that's the probability of success p to the power m, the number of successes we're interested in. And then finally multiplied by 1 minus p, that's the probability of a failure, to the power n minus m, and that's the number of failures that you'd be looking at. So that's our formula for the probability of m successes in n trials. Now, just to recap on that n choose m thing there, you can see down here I've written out what that is. So n choose m is given by n factorial over m factorial times n minus m factorial. And just to cover off on what we mean by factorial, an example would be 3 factorial. It's just multiplying the numbers from 3 down to 1. Okay, so 3 factorial is 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1, and so on, depending on what integer you put in there from this previous page. Okay, so let's check out an example. We're asked to find the probability of rolling 3 ones in 5 rolls of a standard 6-sided die. So I'll start off by checking that I've got a binomial situation first of all. So let's think about it. We've got that we can either have a roll of a 1 or a roll of something else. So we can think of those as success and failure. Success is rolling a 1, failure is not rolling a 1. It's anything else other than a 1. So that sounds good to start off with. When you roll a die, the outcome of one roll doesn't impact on the roll of the next, and so on. So each roll is independent, all good. The probability of our success rolling a 1, so it's a 6-sided die, so the probability is going to be 1 on 6. And the probability of not rolling a 1, that's everything else, that's going to be 5 on 6. And that stays the same throughout every roll of such a die. So probabilities stay constant. The other thing is we have a fixed number, 5 rolls, a fixed number of trials. So we can conclude that this is a binomial situation. So we can model it using our formula. Okay, so the first thing I want to do is to set myself up. I'm going to define my variable. So I'm going to say let capital X be the random variable that representing the number of ones that are rolled when a die is rolled 5 times. Okay, it's a bit of writing, but it's just setting the problem up so that we've got some notation and we understand what we're talking about. Okay, noting that we've checked it's a binomial situation, then we can then go ahead and use our formula. So we can say that the probability that that x variable is equal to 3, so in other words the probability of rolling 3 ones in 5 rolls of a standard 6-sided die, that's going to be given by 5 choose 3, so n equals 5 and m is equal to 3. We're going to multiply that by 1/6 to the power 3. That's our probability P of success is 1/6, and we want 3 of those. And we're then going to multiply that by 1 minus 1/6 to the power 5 minus 3. So that's the other outcomes. That's the failures, which can happen 2 times. All right, so we can just go through and calculate that then. Evaluate it. 5 factorial over 3 factorial times 5 minus 3 factorial. That's our 5 choose 3 times 1/6 to the 3 and 5/6, 1 minus a 6th to the 2. Okay, now that first one, 5 factorial over 3 factorial times 5 minus 3 factorial. You can do that on your calculator if you like, or you can actually work that through by hand. You should find that that comes down to 10. And then the 1 on 6 to the 3, 5 on 6 to the 2 is going to be approximately, so I'll change that, 0.0032. And finally, evaluating that out, 0.032. So the probability of rolling 3 ones in 5 rolls of a standard die is pretty unlikely, 0.032. There we go. So that is an example of calculating binomial probability. Of course, the problems get more involved than that, but that's the basis of them all. You can do things like, how many, what's the probability of getting more than 3 ones in 5 rolls, or at least 3 ones, and those sorts of questions. But that's the basis for those kinds of problems.